One of the things that we still have to do for week 10 is to do some word problems where we have to find an absolute max or an absolute min. And in this first video, I have a fun mathematical problem, and then I will make one more video with a word problem that has a biological application. So I'm showing this slide again, mostly just to remind ourselves of where we are. And so we're looking for an absolute max or a min for a continuous function of two variables. And we do that on a closed bounded set, and the regions that we're interested in this particular course are basically triangles and rectangles. So we'll stick to regions such as rectangles and triangles in this course. If we want to do more funky sets like circles or something like that, then we need some more mathematical machinery, which is beyond the scope of this particular course. All right, so the two things that we have to remember is that absolute maxes and mins can occur at critical points on the interior of the set, or they may occur on the boundary of the set D. So we have to make sure that we take a look at both of those. So the word problem that I have for you is to find three numbers, positive numbers, whose sum is 100 and whose product is a maximum. So first of all, the very first thing that we need to do is give some labels to the numbers. So I'm going to call them X, Y, and Z. And then as soon as you have that, then you know that the product is going to be X, Y, Z, and we'll call the product P. So what we need to do is we need to maximize. So this is to be maximized, subject to the constraint. So we're given that the sum of those numbers has to be 100. So that tells us that X plus Y plus Z has to be equal to 100. I'm going to rewrite that. I'm going to say, well, that is equal to, Z is equal to 100 minus X minus Y, because that allows us to rewrite P as a function of two variables. So this constraint allows us to rewrite P in terms of two variables. I'm going to write it in terms of X and Y just because that makes it more familiar. You could choose to write P in terms of Y and Z and replacing X with 100 minus Y minus Z. So that's totally fine. So in terms of two variables, in particular, P, which was X, Y, Z, is now equal to XY times 100 minus X minus Y. And that is equal to 100xy minus x squared y minus xy squared. Okay, so that looks like a very familiar function. That's very similar to the types of functions that we have optimized in our previous examples. So we are looking for the absolute maximum of the surface P, which really is a function of X and Y, and the function that we found is 100xy minus x squared times y minus xy squared. Okay, now I need to make a note that I'm not calling f of xy equal to z. So let's not call this z, because it's not the same z as this z over here. So let's not call this z here to avoid confusion with the label for one of our three numbers. Okay, and that's of course this z over here. So I've called it p instead. All right, so let's take a look. There are some other implicit constraints that stem from the requirement that x and y and z all have to be positive. They all have to be greater than 0. And so really, that tells us that x has to be greater than 0, but also that x has to be less than 100, because as soon as x is equal to 100 or larger, that then says that y or z have to be 0 or negative, and that's not allowed. So x has to stay between 0 and 100. Similarly, y has to stay between 0 and 100. And moreover, the sum of x and y has to lie within 0 and 100, because otherwise z is a negative number, or 0 possibly. And so these three constraints that I've written in green translate into this yellow region. And the boundary for this yellow region are the lines L1, or the line segments L1, L2, and L3. So we are not allowed to choose points on L1 and L2 and L3, because on L1, for example, y is equal to 0, which is not allowed. But so the boundary is just a nice way to delineate what that yellow region is. All right, so actually let me also make a point. So note, for this problem, the maximum of p cannot occur on the boundary. Composed of L1, L2, and L3. So actually on this boundary, we have that the product is equal to 0, since 1 of x, y, z is equal to 0. So in particular on L1, y is equal to 0 here. On L2, x is equal to 0. And on L3, z is equal to 0. Okay, and then right away that says that p is equal to 0. Similarly, if y is equal to 0, p is equal to 0, and when x is equal to 0, p is equal to 0. And that's certainly we can do better than that. Just pick x to be 1 and y to be 1, then z is equal to 98, and the product of those three numbers is 98. So definitely you're going to have bigger products on the yellow region. Okay, so that actually means that it suffices to focus on the critical points in the interior of the triangle that I drew on the previous page. So we know how to do that. We find the first partial derivatives of p. So here I've reminded you of what p is. P is 100xy minus x squared y minus xy squared. And to find the critical points, first thing we have to do is find some first derivatives. So that p dx is equal to 100y then, minus the derivative of x squared times y with respect to x is 2xy, and the derivative of xy squared is y squared. The partial of p with respect to y is 100x minus x squared, and then from the last term I'm going to get a 2xy. And both of those partial derivatives have to equal 0 simultaneously. So we need to solve simultaneously. I know I'm making a really big deal of that, but that's because this is where we often see incorrect solutions. So let me first of all work with the first equation. So let's call this the first equation. This is the second equation. So 1, what does that say? Well, I can, there's only one x in the middle term there. So that means I can write x in terms of y. So the first step would be to write 2xy is equal to 100y minus y squared. but that is equivalent to, let's divide both sides by y, so 2x is equal to 100 minus y. We know that we're not dividing by 0 because y cannot equal 0. And then that would be equivalent to x is equal to 50 minus y over 2. And then let's substitute this into the second equation to give the following. So I have 100x, so that's 100 times 50 minus y over 2 minus x squared. So that's minus 50 minus y over 2 squared minus 2x times y. Now I still have 2x, it's 100 minus y, so it's 100 minus y times y, and that has to be equal to 0. So that looks like we're going to get a quadratic in y, so let's work this out. Actually, you know what, I'm going to leave that as an exercise. So I'm going to leave this as an exercise for you to do. That saves us a little bit of time, and I'm 100% confident that you can do this. And when the dust settles, you end up with 3y squared minus 400y plus 20,000 is equal to 0. Notice that actually one of the things that I have done is I've multiplied, so this involves multiplying the entire equation by 4. That gets rid of the pesky fractions that come in by taking by having y over 2 in there in the middle term and by squaring that. So multiplying the entire equation by 4. Okay, so this is just a quadratic, and we know how to solve quadratics. So I'm doing that on the next page. So I'm just reminding you of that quadratic formula at the top of the page in green. And so now that quadratic formula from the previous page is repeated over here, and I've already worked through this. I know that you can all do this, and then let's pick up to where we are at the moment. So there are two values of y that you can get, but the first value, y equals to 100, must be discarded, because as soon as y is equal to 100, we cannot have x and z equal to 0. Okay, and then we can accept the other solution, that y is equal to 100 over 3. As soon as we know that y is equal to 100 over 3, then we can calculate x. Right? What is x? Well, x is 50 minus y over 2. And when you substitute this in, 50 minus 100 over 3 divided by 2, you end up with 100 over 3 as well. And then you can calculate what z is. Z was 100 minus x minus y, and you work through that, and you also end up with 100 over 3. Okay? So, to summarize, the product is maximized when x and y and z are all equal to 100 over 3. And the maximum product is P, which is then x, y, z, which is 100 over 3 cubed. And if you put that into the calculator, you basically end up with 37,037 with a few decimal digits, but those are not really all that important. Okay, I don't need the second derivative test, because it's the only critical point there. We know that the maximum is not going to occur on the boundary; it has to occur on the interior. All right, I've visualized this as well on the next page with Wolfram Alpha. So I've graphed the surface. I've stuck with graphing, showing the surface for x between 0 and 50 and y between 0 and 50. And that's mostly because this is the interesting region. Otherwise you don't see the maximum. Otherwise it all flattens out if you plot from 0 to 100. And so the maximum is sitting at 100 over 3. It's about 33.3 or so. And so you can see that on the surface plot on the left, you indeed have a local maximum. And on the contour plot on the right-hand side, the maximum is, again, you can see that it's sitting right in the middle of that little oval there at when x is equal to 100 over 3 and when y is equal to 100 over 3. All right, so here we've done our first word problem. I want to do one more word problem, so hang on for one more video for week 10, and then that will complete the week 10 material. Bye!